Okay, so we have seen similarity transformations. So in this lecture, we'll look at a special kind of similarity transformation, which takes a matrix and which makes it diagonal, right? So that's goes by the name of diagonalization of matrices. Okay, let's consider an n by n matrix A. I'm explicitly writing it out. It has all these elements of this matrix. There are n squared of these. So I am looking at a matrix which has n linearly independent eigenvectors, right? I'm not saying it's linearly independent column vectors. That's a different concept. I'm talking about a matrix with n linearly independent eigenvectors, right? So if you recall from several lectures ago, we looked at certain matrices which we called defective matrices, right? Although every matrix is guaranteed to have exactly the number of eigenvalues as its dimension, although some of these eigenvalues may be repeated, but there is no guarantee that every matrix will have eigenvectors which will complete the space, right? There are matrices which are called defective matrices, but we will talk about this a little bit later. But for the purpose of this lecture, let's look at matrices which are which have n eigenvalues, lambda 1 all the way up to lambda n, right? So some of these could be repeated, there's no problem with that, but the key requirement is that all these n eigenvectors are linearly independent. If this happens, then let's collect all these eigenvectors. So you have n linearly independent eigenvectors. We will notate this as xi, these coefficients si1, si2, so on, all the way up to sin. Then we have this defining property of these being eigenvectors is that A acting on xi should give you lambda I acting on xi. So if you stack them all together, right? So now you see the point of the previous lecture where we looked at properties of matrices formed by stacking together such linearly independent vectors. We saw that since these are all linearly independent column vectors, so you have n linearly independent column vectors, each of these column vectors is linearly independent, therefore necessarily S is an invertible matrix. So this is important for us, as you will see. So let's consider its inverse and denote it as S inverse as usual. Now the product of these matrices A times S is important. So A times S is, there is this matrix A, this is what we started with, and then we just stack together all its n linearly independent eigenvectors and form this matrix. So we can look at the product of these two matrices, and then we see that in fact this product is something that we can work out in a straightforward way, because what is the first what is the effect of multiplying this matrix with the first column vector? If I look at this column vector, it's really A acting on x1, so that should give me lambda 1 x1, and so I can write lambda 1 x1 as lambda 1 s11, lambda 1 s21, all the way up to lambda 1 sn1. And similarly, if I take this entire matrix and multiply by the second column, I must get back the same column, but now with these factors lambda 2 in here, lambda 2, so on. And likewise for every column. And for the final column, we see that if I multiply this entire matrix with this column, the nth column, s1n, s2n, all the way up to snn, will give me back the same column, except that I have to tag along these factors lambda n. So as is something that I can immediately work out because of what I have chosen S to be. Now we also know that S inverse exists, so S inverse times S is equal to I. So let us sandwich A between S inverse and S. So let's work out S inverse AS. So S inverse S is equal to I. So S inverse AS. So we see that when we do AS, you basically get S, but every column has an extra lambda 1 there, right? You can convince yourself that all this does is if I multiply S inverse with AS instead of S inverse with S, I will still have a diagonal structure, but now I'll have to put in lambda 1 here, lambda 2 here, all the way up to lambda n, right? This you can see because S inverse acting on S is I. So if you take the first row and multiply by the first column, it must give you just 1. But now I have a lambda 1 here, so it will give you lambda 1. So likewise lambda 2 and so on up to lambda n. So what we have done just now is something called diagonalization, right? So we have managed to do a similarity transformation on our original matrix A, and we have obtained a diagonal form for it, which all of whose elements are just the eigenvalues of your matrix A, right? So if you could find such a similarity transformation, you could use this to get to the eigenvalues of this matrix. But oftentimes, to find the eigenvalues of the matrix, you can just go to the characteristic equation, come up with a polynomial, find its roots. You have another way of finding the eigenvalues, right? But diagonalization involves finding this similarity transformation, which puts your matrix in a very nice form, right? We will see later that this has important applications. Diagonalization of a matrix, when it is possible to diagonalize a matrix, gives you some, is a very nice thing to do, because you can compute lots of properties of your matrix, which are in your matrix, are understood in terms of the eigenvalues, but also these the similarity transformation, which diagonalizes the matrix, also contains a lot of information, because all the eigenvector information is also enshrined in it. So we have talked a lot about unitary matrices, right? So if your n vectors are not only linearly independent but also orthogonal, then in place of S inverse A, S, you'll just have U dagger A U, right? So if in addition to, if your eigenvectors of your matrix, original matrix, you had not only x a xi giving you lambda I xi with all these xi being linearly independent, right? There is a shorter class of matrices whose eigenvectors are not only linearly independent, but they are also orthogonal to each other. We have looked at some of these matrices, right? And they appear in many important contexts, like in quantum mechanics, right? Hermitian operators, for example, right? And or there is a way to, if in the presence of degeneracy, it is still possible to find a set of vectors which are eigenvectors of your matrix and which are orthonormal. When you have such a scenario, not only do you have a similarity transformation, but you have a special kind of a similarity transformation. That's a unitary transformation, which imposes some more constraints on the nature of nature of your final diagonal matrix of your system, right? So unitary transformation is a special class of similarity transformation, and there is another kind of transformation which is a special kind of unitary transformation, and that is called an orthogonal transformation, when you are dealing with just real numbers, right? So U dagger is the same as just U transpose. If all the elements of your matrix are real, then you get an orthogonal transformation, which is another further special class of unitary transformations or unitary matrices. Okay, so that's all for this lecture. Thank you.